Hello, everyone. Welcome to the lecture on ionic covalent compounds, bonding, and writing chemical formulas. We'll start out by talking about oxidation states and apparent charges. So a lot of times we say that a species has a charge when actually we're referring to an oxidation state. That is a charge that an atom or another species will gain as it is forming a compound. It doesn't carry that charge around like an ion would all the time. But we take a shortcut and we call it a charge, even though it's really an oxidation state. In group 1A on the periodic table, all of those species have a +1 oxidation state or a +1 charge when they're getting involved in a reaction with another species. Hydrogen is the special case. Hydrogen, if you see it written first in a chemical formula, is associated with a positive oxidation state. Well, if you see it written last in a chemical formula, like in NaH here, it is associated with a negative oxidation state. Group 2A all have, so that is the alkaline earth metals, all have a +2 oxidation state. Group 3A all have a +3 oxidation state. And then there are certain species that have a given oxidation state that doesn't change even though they might be considered transitional. That is, they're not representative, but they're in the B group. And that would be silver and zinc and cadmium. Silver always has a +1 oxidation state, zinc always has a +2 oxidation state, and cadmium always has a +2 oxidation state. And we'll talk about why that is later after you've learned some quantum mechanics. Aluminum has a +3 oxidation state all the time, but those species that are in the same group, column, or family with aluminum typically do have a +3 oxidation state. And then group 7A have a -1 oxidation state. And when we start naming compounds, you're going to see that the suffix of those species in group 7A changes to IDE rather than INE. Group 6A all have -2 oxidation states. Group 5A all have -3 oxidation states. And Group 4A all have -4 oxidation states. And these aren't particularly things that you have to memorize, but I would label the top of the periodic table that you have. Keep a periodic table and maybe label the top of it with these oxidation states until you get used to them and until you start to understand why that's the case. So we'll start working on why that would be the case by looking at this periodic table and spelling out how does a specific species end up with a specified oxidation state in the entire group, column, or family. And it is because, as we talked about in the last lecture, that all these species are striving to be like the Nobel gas that is closest to them. For example, fluorine over here strives to be like neon and have the electron configuration that neon has. Well, neon with an atomic number of 10 has 10 protons, and because it's neutral on the periodic table, also has 10 electrons. Fluorine, on the other hand, has an atomic number of 9 and therefore has 9 protons, and because it's neutral on the periodic table, fluorine has 9 electrons. And so for fluorine to get the electron configuration of neon, it would have to gain 1 electron and then would have 10 electrons. And so when fluorine becomes reactive, it's seeking to find another species to react with that has 1 electron to hand over to it. If we look at the other end of the periodic table, say we look at sodium. Sodium has an atomic number of 11. And so with an atomic number of 11, sodium has 11 protons, and because it's neutral, since it's on the periodic table, we know that, also has 11 electrons. Now, the chemically closest Nobel gas to sodium is also neon. And neon has, as we said, 10 electrons. So for sodium, to get the electron configuration of neon, sodium would have to give up an electron. And so you would have 11 electrons minus 1 electron would give us a total of 10 electrons. And that is the electron configuration of neon. Now let's talk about both fluorine and sodium. And think about if these two species were going to react with one another. Sodium happens to have 1 electron it can give up, and fluorine happens to need 1 electron. Sodium gives up 1 electron, it gets the electron configuration of neon. Fluorine accepts 1 electron, it gets the electron configuration of neon. So if sodium were approaching fluorine, then what sodium could do is essentially transfer an electron to fluorine. That way sodium is giving one up, fluorine is accepting one. In transferring that 1 electron, sodium now becomes Na+. In accepting that 1 electron, fluorine now becomes F-. And so we have a situation where both of them now have this perfect octet. One with a negative charge, one with a positive charge, and they can form a neutral compound. +1 - 1 gives us NaF, or sodium fluoride. Again, the INE on fluorine is converted to IDE when we form a compound with one of those halogens. It turns out that the representative elements on the periodic table will all behave this way so that they can react and gain the electron configuration of the noble gas that is closest to them. So what if we had a reaction between sodium, which is a species in group 1A, and chlorine, which is a species in group 7A? They would form sodium chloride. What about a species in group 2A, like magnesium, and a species in group 4A, like carbon? So if we want charge neutrality by looking at these oxidation states that we have here, we're going to need 2 magnesiums in order to neutralize this 1 carbon with a 4-. So these 2 magnesiums give us 4+, and this 1 carbon is 4-. 4 - 4 gives us charge neutrality, and the way we would write that is Mg with a subscript 2 because we have 2 magnesiums, and C, and there's no subscript. Whenever there's no subscript, we know that means 1. And there's no charge written on this complex because it's neutral. The +4 and the -4 canceled each other out. What if we have something like aluminum oxide, on the other hand? So the aluminum has a +3, and the oxygen has a -2. Well, in this case, we need to find a common factor for a +3 and -2, and that would be 6. So if we use 6, we need 2 aluminums with a +3 to give us +6, and we need 3 oxygens with a -2 to give us -6. So here we have +6, here we have -6. They cancel each other out or neutralize each other, and we end up with 2 aluminums, which we write with an aluminum with a subscript 2 to show that, and 3 oxygens. Now there's a little shortcut that you can take, but you've always got to go back to the basics and use this math to make sure that you're at the lowest common multiple. But the shortcut that we can use is we have aluminum with the 3 plus, and we have oxygen with the 2 minus. And the little shortcut that we can use is that we put the 3 right here, and we put the 2 right here. That's our shortcut. So again, we end up with Al2O3. But I just want to double check and make sure that I have the lowest common multiples, 2 and 3. So I may want to go back to this factor of 6 and just make sure. Polyatomic ions are formed through loss or gain of electrons from a group of atoms, and that group of atoms is held together by covalent bonds. So for example, if we talk about sulfite, SO3, 2 minus, the sulfur and the oxygens are held together by covalent bonds. And as we drew Lewis structures, we could see that. You're going to be drawing some more Lewis structures, and so you're going to be able to see that even more. Covalent bonds have to do with sharing of electrons. We just looked at an ionic compound between sodium and fluoride, or magnesium and chloride, and we had transfer of electrons. But with covalent compounds, we are sharing of electrons. Monoatomic ions are formed from a single atom that has a loss or gain of electrons. And so we're not talking about oxidation states when we talk about an ion. We're talking about a species that exists, for example, H plus, exists in acidic solution as an H plus. It's not just gaining that positive charge as it's approaching another atom in order to react. Ionic compounds are involved in transfer of electrons, and this is the main thing that you need to remember. If it's an ionic compound, it's involved in transfer of an electron from a metal to a nonmetal. So for example, if we had magnesium, which is a metal, reacting with chlorine, which is a nonmetal, we could form magnesium chloride by transfer of an electron or 2 electrons. Magnesium reacting with nitrate, we could transfer electrons, we would form magnesium nitrate. Or ammonium acting with sulfate, we would form ammonium sulfate. Let's look at how that works. And so let's look at magnesium and chlorine to start with. Magnesium is in group 2A. So because magnesium is in group 2A, magnesium has to give up 2 electrons so that it can get the electron configuration of neon. Magnesium has an atomic number of 12. Neon, of course, atomic number of 10. So in order for magnesium to get the electron configuration of neon, it's going to have to lose 2 electrons. Then it can have the electron configuration of neon with 10 electrons. If magnesium has to give up 2 electrons, that means that it has to have an oxidation state of 2 plus when it transfers those electrons. Now let's think about chlorine. Chlorine is closest to argon. Chlorine has an atomic number of 17. Argon, on the other hand, has an atomic number of 18. So in order for chlorine to get the electron configuration of argon, it's going to have to gain 1 electron. If it gains 1 electron, it's going to have an oxidation state of -1 when it's getting involved in a reaction with another species. So in this case, we're going to need 2 chlorines that are accepting these 2 electrons that magnesium is giving up in order for this reaction to occur. That means we have 1 magnesium and 2 chlorines in our compound that we form called magnesium chloride. Now, the reason that you have to start memorizing all of these polyatomic ions, because if you don't memorize these polyatomic ions, you would not know that nitrate, so if you have this memorized, you can say right away, this is nitrate, and nitrate's chemical formula is NO3-. This is sulfate, and sulfate's chemical formula is SO42-. If you're just given the names, you're going to have to derive the chemical formulas in order to write the compound that would form between, for example, magnesium and nitrate, or between ammonium, which is another polyatomic ion you have to memorize with the name, ammonium and sulfate, for example. So again, we know that magnesium, because we just looked at it in the previous example, has an oxidation state of +2 because it's got to give up 2 electrons in order to achieve the electron configuration of neon. So +2, while nitrate has a -1 charge associated with it, that means that we're going to need 2 nitrates in order to form a compound and get charge neutrality. So if you're looking at what we're doing here, we're after charge neutrality. We have a +2, we need a -2 to get neutralization here. This way we have 1 magnesium, and now because we have nitrate, we have to make sure everyone knows that we're talking about an entire NO3-. So we're going to put NO3 in these parentheses, and we're going to put a 2 outside of the parentheses to show that we have 2 of those. Notice I don't write any of the charges because the charges have all neutralized one another. I'm going to leave ammonium sulfate for you to do on your own later. So what are the rules for assigning oxidation numbers? The rules for assigning oxidation numbers for elements in the free state are always oxidation number of 0. Metals typically have a positive oxidation state, and they're by convention written first in a chemical formula. The oxidation state, or we could also call it the oxidation number. So just try to keep in mind that on a test, you may see oxidation number, or you may see oxidation state. Those 2 terms are interchangeable. The oxidation number of hydrogen is typically +1. The oxidation state of oxygen is typically -2 in compounds. And so what they're saying to you is that these are pretty foolproof. And if you're trying to determine what the oxidation state is of an unknown that you have in the compound, and you have either a hydrogen or an oxygen, you can always calculate the charge contribution of those 2, one of those 2 species, and then calculate the oxidation state of the other species. You sum the charges in a neutral compound to 0, and that's what we did on the last slide. The oxidation number, or the oxidation state for monoatomic ions, is equal to the charge that's on the ion. And the sum of charges in a polyatomic ion is equal to that charge. So we sum all the oxidation states in a polyatomic ion and set them equal to the charge that's on the ion. So let's try that. Let's calculate the oxidation state, or the oxidation charge, of the nitrogen in the polyatomic ion nitrate. And we know, because we said that oxygen is foolproof. So oxygen, unless you're in a peroxide, which we're not in a peroxide here, oxygen is going to have an oxidation state of -2. So we know that we have 3 oxygens. So we have 3 times the -2 charge, and that gives us -6. So -6 for the oxygen plus whatever the charge is of the nitrogen is equal to -1. -1 is the charge on the entire complex. So we can literally add 6 to both sides, and then the oxidation state, or the charge that's on the nitrogen, is +5. So let's calculate the oxidation state, or again, apparent charge of sulfur in sulfate. So again, we have oxygens, and we know oxygens are foolproof. So we have 4 oxygens, and we know that the charge on each oxygen is -2. So that gives us a total of -8 for the oxygens. That means whatever the sulfur is plus the -8 charge contribution by the oxygens is going to equal -2. We can just add 8 to both sides of this equal sign, and then the sulfur is equal to 8 minus 2, or +6. In terms of ionic bonding interactions, again, I just want to keep reiterating, if it's an ionic bonding interaction to form a compound, we're talking about transfer of electrons. Remember, if it's covalent, we're talking about sharing of electrons. Those things need to be pretty much ground into your memory bank. So transfer of electrons is going to require the presence of 2 elements. In order to transfer an electron, you have to have an element that's going to be a donor, and you have to have an element that's going to be an acceptor. The metal is going to donate the electron because metals give up electrons in order to have the electron configuration of the Nobel gas closest to them. Nonmetals accept electrons in order to have the electron configuration of the Nobel gas closest. The ratio in which positive and negative ions combine is that which achieves charge neutrality, which we have been working on examples since the start of this lecture. The exception is polyatomic ions. And so with polyatomic ions, as we looked at, we're more focusing on what is the charge that's on the ion itself. Formula units for ionic compounds, and I just want to make sure you're aware, we're talking about ionic compounds. This doesn't pertain to covalent compounds. We have the smallest whole number ratio when we talk about ionic compounds. For covalent compounds, you may or may not have the smallest whole number ratio. So let's talk about potassium and sulfur. Potassium, as you know, is in group 1A on the periodic table, so it has 1 valence electron. Sulfur is in group 6A on the periodic table, so sulfur has 6 valence electrons. Let's talk about how we would form this ionic compound with potassium, a metal, and sulfur, a nonmetal. So I've put a small portion of the periodic table so that we can just reiterate and review how this happens. So we start with potassium, which is over here on the left. Potassium has atomic number 19. With atomic number 19, that means that potassium has 19 protons and 19 electrons. Now, if we look for the Nobel gas that is chemically closest to potassium, that would be argon over here. Argon has atomic number 18. That means that argon has 18 protons, and more importantly for us right now, because we're talking about chemical reactions, argon has 18 electrons. Now, argon is stable, it's inert, it's a noble gas. Every other element on the periodic table is reactive until it has the electron configuration of a noble gas. The noble gas closest to it is the most energetically favorable because Potassium, for example, only has to give up 1 electron to get the electron configuration of argon. So 19 electrons minus 1 electron equals 18 electrons, and the electron configuration of argon for potassium. In giving up that 1 electron, though, potassium now becomes K plus with an oxidation state of +1. Let's have a look at sulfur and see how sulfur behaves. Sulfur is closest to argon as well. So sulfur has an atomic number of 16. That means sulfur has 16 protons, and because it's on the periodic table, it's neutral. Also has 16 electrons. But sulfur wants to have the same electron configuration as the noble gas that's closest to it. In order to have that electron configuration, sulfur has to gain 1, 2 electrons. So 16 electrons plus 2 electrons gives us 18 electrons, and now sulfur has the electron configuration of the noble gas that's chemically closest to it, and that is argon. So how does all of this work in terms of now writing the chemical formula? Well, we see that we have potassium with a +1 oxidation state, and since sulfur has gained 2 electrons, we have sulfur with a 2- oxidation state. In order to get charge neutrality, we have 2 negative charges. We need to have 2 positive charges. We write the metal first by convention, and so that is going to be K2, and then the non-metal is written last. K2S is potassium sulfide. Because remember, we changed this suffix to IDE. Covalent bonding is sharing of electrons, and so that needs to be grilled in. When we have covalent bonds, we have shared electrons. When we have ionic bonds, there is transfer of electrons. So we have 2 nuclei essentially that are attracted to the same electrons, and they share the same electrons. So if we had H2, for example, these 2 hydrogens would be sharing these 2 electrons that each one has donated to that covalent bond. Covalent bonds can form between 2 similar or identical elements. And so O2 has 2 identical elements. NO2 has 2 different similar elements because they're both non-metals. Remember, with ionic bonding, we need a metal and a non-metal. Because we need a metal to donate the electrons, we need a non-metal to accept the electrons. Here we can use 2 non-metals because they're sharing electrons. These are referred to as molecular compounds. So we can call them molecules, molecular compounds, or covalent compounds. Those are all interchangeable terms for the same type of compound. The units in ionic compounds are ions. The units in covalent compounds are molecules. Covalent compounds contain both bonding and non-bonding electrons, and we saw a lot of that in the last lecture when we were drawing Lewis structures. Bonding electrons are pairs of valence electrons that are shared between the atoms in a covalent bond, and each covalent bond has 2 electrons in it. Non-bonding electrons are pairs of valence electrons that are associated with an atom that are not involved in electron sharing. So let's look at a couple of situations where we have electrons that are being shared and electrons that are not being shared. And I'm going to leave most of these for you to draw on your own, but there are a couple of them that I want to draw just because they might be a little bit different, or they might show both shared and unshared electrons. So let's start with NO2. And as with before, when I showed you in the last lecture, we're going to look at the octet and we're going to look at the valence. And so for nitrogen, the octet is 8. For oxygen, the octet is also 8, and there are 2 of them we can't forget. So that's a total of 24. The valence for nitrogen is 5, and the valence for oxygen is 6, and we have 2 of them we can't forget. So that is a total of 17. 12 plus 5 gives us 17. So the difference here is equal to 7. 7 divided by 2 is going to give us some fraction. And so we know right now that the math has broken down, because a fraction is not going to give us the bonding pattern that we're looking for. So that means that we're going to use this 17 when we draw this structure out. That's our valence electrons. So we have nitrogen, and it's flanked by 2 oxygens. And we know that nitrogen likes to have 3 bonds, and we know that oxygen likes to have 2 bonds, because if we went back to their Lewis dot structures, here is nitrogen. Let me erase that line. Here is nitrogen, and here is oxygen. So oxygen wants to have a bond here and here, nitrogen here, here, and here. So oxygen again likes 2 bonds, nitrogen likes to have 3 bonds. We could do that by putting a bond here, giving that oxygen 2 bonds, and this gives nitrogen, the other oxygen, 1 single bond. That uses up 2, 4, 6 out of the 17, and so we have 11 more electrons to put around this structure, and so we can put 6 of them here. 7, 8, 9, 10. Sorry, we need to take 2 away from that side. I have 2 too many. So that gives us 2, 4, 6, 8, 10. And then we have 1 more, which we could put on the nitrogen right here. Now let's calculate the formal charge and see what this structure looks like in terms of formal charge. So this oxygen over here has a valence of 6, and it has 7 electrons in direct contact with it, so that gives it a -1 formal charge. This oxygen on the other side, 6 is the valence, minus 6 electrons in direct contact, which gives it a 0. And then this nitrogen is 5 minus 1, 2, 3, 4. And so that gives it a +1. So +1 minus 1 is not too bad because they're adjacent to one another. But what if we could change this structure a little bit so that we had all zeros? It would be an even better structure then. And one of the ways that we can do that is to give the nitrogen 4 bonds, which it's not crazy about, but that would give both oxygens 2 bonds. So if we had nitrogen in the center and 2 bonds to each of the oxygens, and I'm just thinking about this oxygen over here having a formal charge of 0 and giving a formal charge of 0 to the other oxygen by doing the same thing with it. So we have 1, 2, 3, 4, 5, 6, 7, 8. There's our electrons. And then we put an electron here on the nitrogen. And let's count because we're after 17, remember. So this is 2, 4, 6, 8 electrons in the bonds. And then the lone pairs are 10, 12, 14, 16. And if we put that electron right there, that gives us a total of 17, which is our valence. And now let's calculate and see if we can get formal charges that are all 0. So this one is 6 minus 2, 4, 5, 6. That's 0. And this one over here is exactly the same. And then the nitrogen is 5 valence minus 1, 2, 3, 4, and 5 with this one up here. And so that equals 0. And so this structure now has zeros per formal charge all the way around. And it turns out that this is the better structure because the formal charges are all 0. Now let's look at, and that's an odd case because you have that one electron on the nitrogen. It's not paired, but that's still a valid Lewis structure. Let's look at water, which is a Lewis structure that I had asked a lot of you to draw on the initial assessment, which you didn't lose any points for. I just wanted to see where you were at. So if we have the octet electrons and the valence electrons, then hydrogen, there's 2 of them, that's going to be 2 times 2. And there's 1 oxygen, so that's going to be 8. The valence for hydrogen is 1, and of course there are 2 of them. And the valence for oxygen is 6. So 8 and 4 gives us 12, and then 6 plus 2 gives us 8. If we take the difference, we get 12 minus 8, which is 4. Divide that by 2 electrons that are in a covalent bond, and we get 2 bonds. So oxygen is our central atom, and we have a hydrogen on either side of it. And then we have 8 valence electrons. We've used 4 of those electrons for bonding. That leaves us with 4 electrons to distribute around the structure. And it turns out that the oxygen needs all 4 of them in order to have a perfect octet. And now let's calculate the formal charge really quickly. Hydrogen has a valence of 1 minus the 1 electron that it has here associated with it directly. So that's a formal charge of 0. And this hydrogen is chemically equivalent, so it has the same formal charge. Oxygen has a valence of 6 minus the 6 electrons that are in direct contact with it, gives it a formal charge of 0. And so this is a valid Lewis structure. Now there are a few other structures there for you to practice later. Let's talk about single, double, and triple covalent bonds now. And so I'm going to leave these 2 Lewis structures for you to draw later. They have all single covalent bonds, and every covalent bond has 2 electrons in it. Let's work on one of these, and I'm going to work on formic acid because it's a little bit more difficult than the other 2. So again, we're going to do the same calculation we've been doing. We need octet electrons and valence electrons, and we take the difference between them. So there are 2 hydrogens in this structure. Just because they're not right together doesn't mean there aren't 2 of them. And so the octet is going to be 2 times the 2 of them. There are also 2 oxygens in this structure. And so the octet is going to be 8 times the 2 of them. And then there is 1 carbon, and so that octet is going to be 8. So we have 24 plus 4 gives us a total of 28, and then the valence for the hydrogen is 1, and there are 2 of them. The valence for the oxygen is 6, and there are 2 of them, and the valence for the carbon is 4. So 2 times 6 gives us 12, plus 2 is 14, plus another 4 is 18, and we take the difference That gives us 10. We divide the 10 by 2 electrons because there are 2 electrons in each covalent bond. That gives us 5 bonds. And now we'll draw the structure. And I'll just do it in a different color so that it's not all running together here. So we have a central carbon. And then that carbon, remember, has to have 4 bonds. So it is bonded to 2 oxygens and a hydrogen. And then remember, hydrogens like to hang around with oxygens, but the carbon still doesn't have its 4 bonds. If we get this oxygen here, so let me just change pen color so we can talk. This oxygen here has 2 bonds, but this oxygen up here only has 1 bond. So if we give that oxygen up top the other bond, we now have 5 bonds. 1, 2, 3, 4, 5 bonds, which is what we said we needed. We now have 5 bonds, and we just need to calculate based on our valence 18. We used 10 electrons for bonding, and so we have 8 electrons left to distribute around the structure. So the hydrogen has a duet, so it's perfectly fine. The carbon has 2, 4, 6, 8 electrons surrounding it in bonding interactions. This oxygen that this arrow is pointing at is electron deficient. It only has 2, 4, so we're going to give it 4 more. That gives it 8. And then the other oxygen with the arrow pointing at it only has 2, 4. So we're going to give it 4 more so that it has a total of 8. And now we're going to start calculating the formal charge. Sorry, that's my cat leaping across the room here. Okay. So oxygen has a valence of 6, and there are 6 electrons in direct contact with it, so that gives us a formal charge of 0. This other oxygen, valence of 6 again, 2, 4, 5, 6 electrons in direct contact with it, so that gives us a 0. The carbon has a valence of 4. It has 4 electrons in direct contact with it. Formal charge is 0. Hydrogen, valence of 1. It has 1 electron in direct contact with it, so that gives it a formal charge of 0. All of these species have a formal charge of 0, and so this is a valid structure. Now, what if I hadn't have drawn it like this? Well, why don't you sort of think about the other ways that you can draw it? Hydrogens always have to be terminal. So we couldn't have put a hydrogen between the carbon and the oxygen because they always have to be terminal. So this is literally the only way that we could put the atoms together and make sure that the hydrogens are kept terminal. I suppose there's one other way you could have drawn it. You could have drawn it with a carbon and then an oxygen here and an oxygen here and a hydrogen here and a hydrogen here. And you may want to try that. It does give the carbon 4 bonds. Neither one of the oxygens has 2 bonds, but you may want to try that out and calculate the formal charges and see if it works for you. The other type of bonding interaction we can have is a triple covalent bond. And so if we look at, for example, HCN, and again, we want the octet and we want the valence. So the octet for the hydrogen is 2. For the carbon is 8, and for the nitrogen is 8. It's a total of 18. The valence for the hydrogen is 1, the valence for the carbon is 4, and the valence for the nitrogen is 5. So that gives us a total of 10, and the difference equals 8. When we divide that by 2 electrons, we get 4 bonds. So let's think about how we're going to put this structure together. If we have hydrogen terminal, carbon central, and then nitrogen, that's only 2 bonds, but remember, nitrogen wants 3 bonds and carbon wants 4. So if we gave nitrogen 3 bonds by putting a triple bond right here, carbon now has 4 bonds, nitrogen now has 3 bonds. We need to calculate the electrons that will be remaining around the structure. So we have 10 as our valence minus 8 electrons used for bonding. That leaves us with 2 electrons to distribute around the structure. Hydrogen has a duet, it has 2. Carbon has 2, 4, 6, 8, so it's fine. Nitrogen is 2, 4, 6 with the triple bonds, and we give it that lone pair so that it now has a octet. And if we calculate then the formal charges associated with it, hydrogen is 1 minus 1, so that's 0. Carbon is 4 minus 4, so that's 0. And nitrogen is 5 minus 5, so again, 0. All the formal charges in the structure are 0, so this is a good Lewis dot structure. Coordinate covalent bonds are the last thing we're going to talk about. With coordinate covalent bonds, so far with covalent bonds, we have seen the sharing of electrons where each atom donates an electron for sharing. But with a coordinate covalent bond, both electrons are donated from one of the 2 atoms. So each atom doesn't donate an electron. One atom donates both electrons. And this allows an atom with multiple vacancies in its valence shell to share a pair of non-bonding electrons that are donated by the same atom. For example, oxygen has 2 vacancies in its valence shell. So let's consider these 2 different acids, hypochlorous acid and chlorous acid. And let's draw the Lewis structures for each one of them, and then try to make a determination about the structures and where the electrons are coming from. So if we draw, for example, the Lewis structure, and you would normally calculate the octet and the valence, but for the sake of getting through this discussion, I'm not going to calculate all of that. I'm going to draw the structure, the Lewis structure, with a quick calculation in my head, which you will get to the point where you can do that pretty well too. And I want to then highlight where these electrons are coming from. So let's highlight where the electron comes from in the OH bond. This electron comes from the hydrogen. And then let's talk about the electrons that are coming from the oxygen. So we have this electron in that bonding interaction that's coming from the oxygen, and this one, and this one, and this one, and this one, and one more is this one over here. And let's talk about the electrons that are coming from the chlorine. And so there's this one, and this one, this one, this one, this one, this one, and this one. Okay, so how many electrons coming from the chlorine? 7. And that makes sense because chlorine is a halogen. It has a valence of 7. So that makes perfect sense. The oxygen has how many? 6 electrons that the oxygen is donating. And that makes perfect sense because oxygen has a valence of 6 electrons. Hydrogen is donating 1. And that makes sense because hydrogen has a valence of 1. So in other words, each one of these atoms is donating 1 electron to each bond. I know that oxygen is donating an electron to the OH bond and it's donating an electron to the OCl bond, but it's still only donating 1 electron to each of those bonds. Let's talk about what's going on with the other structure, chloric acid on the bottom. So we have H, O, Cl, and O. And we have our 1 electron here from our hydrogen. And then the next oxygen has an electron here, an electron here, 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 and here. So that is 6 electrons, which is the valence of oxygen, so that's fine. And then this is 1 electron, which is the valence of hydrogen, so then fine. The oxygen donated 1 electron, the hydrogen donated 1 electron. Let's look at the chlorine. So the chlorine has 1 electron here, 2, 3, 4, 5, 6. Well, that's odd because chlorine has 7, a valence of 7. So that doesn't entirely make sense. Let's look at the last oxygen. So the last oxygen has 1, 2, 3, 4, 5, 6. So there's all of the 6 electrons for the oxygen. That's its valence. It doesn't have any more electrons. But the chlorine has another electron. And so that must be here for a total of 7. That makes that bond right there different than all of the other bonds because both electrons in that bond were donated by chlorine. In other words, the oxygen on the end did not donate an electron to that bond. Both were donated by chlorine, so both were donated by 1 of the 2 atoms in the bonding interaction, and that makes that bond a coordinate covalent bond. Not just a covalent bond. There is sharing, which makes it a covalent bond, but a coordinate covalent bond. So sharing, but sharing coming from 1 of the 2 atoms involved in the bonding interaction. So that concludes this lecture. Again, if you have any questions, email your questions to me, or better yet, bring your questions to Chem at Night and we can answer them all together.